Okay. So I'm particularly interested in so-called latent variable models. And in latent variable models, we typically express the probability of a data point through marginalization over a vector of latent variables. So we are interested in this conditional probability of x given z, where z is, say, the latent representation, the latent encoding of my data x. And this probability distribution is usually computed by means of some model, typically a neural network. So the neural network is the network that is able to produce x given the latent variable z. So why are we interested in studying generative models? Well, we have a lot of motivation. I think that the most interesting fact is really to understand this generative process that is kind of, I mean, it is really surprising, okay, in the way you are able to generate a high-dimensional, high-resolution image starting from a bunch of latent variables. So is by means typically of small spatial based of convolutions, okay, with a very small kernel is really an interesting point. And we want to improve our knowledge of the latent representation of data. So with these very information that are extracted by these models, and what is what are the information that they use in order to encode the data. And I mean, it's generative modeling, the typical approach in a lot of situations, typically in all the cases where you have multimodal outputs. So you are not confined to a specific output, you have a range of possibility, and you would like to have, of course, to study, to address the distribution, okay, of the possible outputs, and finding, okay, there is a practical issue that is consisting in producing realistic samples from similar, okay, to the kind of data that we have in the training set. There are two major approaches in the latent encoding, the latent variable models, variational encoders and generative adversarial networks. Generative adversarial networks actually are much more important than variational encoders. They also work better, but okay, both of them are actually investigated. And the way that the two classes essentially differ in the way that you train the generator. And in the case of a variational autoencoder, what you do is you couple the generator with an encoder. The encoder is doing the opposite operation, so it's producing the latent representation of x, starting from x. And then you may imagine, okay, how you train both of them together. Namely, you try, okay, to reconstruct the same input that the same data, okay, that you receive as input. So it's basically a variational autoencoder is just trained as a traditional autoencoder. And in addition, you have an important issue that you would like to use the latent space really to assume a known distribution, because this is the prior distribution from which you will sample the values of Z. And so the problem is to bring the marginal influence distribution close to a known prior distribution of your choice. Typically, you take a Gaussian spherical distribution, and to this aim, you add a particular component to the loss function that is this Kullback-Leibler distance. And okay, that's exercising this purpose. In a generative adversarial network, you can do a completely different things. Namely, you couple the generator instead with a discriminator. And the purpose of the discriminator is just to distinguish between real data. Here you have receiving input to real data and the data produced by the generator. So the discriminator really produces a yes/no answer. Okay, this is fake, this is real data. And then they are trained alternatively. And I mean, you train the discriminator trying to, of course, discriminate between real data and the data produced by the generator. And instead, you train the generator just with the purpose of fooling the discriminator. Okay, the generator produces something; it has no knowledge. Okay, what is real or what is not. What his purpose is not to produce something so real, because it doesn't know what real means. Its purpose is just to fool the discriminator. And you have to train them one after the other in order phases in order to achieve the good goal. So there is no deep mathematical reason why a generative adversarial network should work, but they do, and they work really well. There is a stronger background behind the variational encoders. They should work, but they don't. This is something interesting that you could think about. Okay, exploring space. What is the idea? The main idea behind this new field of represent new? I mean, no, it's old, but I mean, the more interesting result have been achieved very recently. Of the field of representation learning. So first of all, the generative process, as any process involving neural networks, is continuous. That means that if you make a small movement in the latent space, this is going to produce a small result in the visible space. So it's very interesting to study, okay, this kind of movements and to understand, okay, how the modification in the latent space is going to be reflected in the visible space. Second point, real-world data seems to depend on a relatively small number of explanatory factors of the variations of the data. And if we understand and we are able to extract these explanatory factors, then we are also able to produce some compressed internal representation of our data. And understanding, okay, this data, these factors of variations, finally helps us to define interesting trajectories inside the latent space, producing desired alterations into the visible space. So here you have a video. I'm not showing you. You can go to it, and it's on YouTube. Okay, you can inspect it by yourself. And there is this idea of latent space interpolation that is very interesting. And you can see how moving in the latent space, in this case, we are interested in producing human faces. Okay, you are able to produce different faces in the visible space and to pass from one to another one. Then this is the so-called semantic investigation, semantic exploration of the latent space, the kind of vector that you want to produce. This is the original image. And suppose maybe now you want to modify the image, for instance, changing the age of the person, or maybe adding glasses, or maybe adding the gender, okay, passing from male to female, or maybe slightly moving, okay, the position, changing the position of the face. These are results achieved, okay, by this kind of, it's not a desiderata, it's a result, okay, a real result. And this is the same, okay, on a different image. How can you achieve this kind of behavior? Well, the idea is relatively simple. You start from the supervised data set. So you have in the visible domain, you have your images, say with glasses and without. You map them back into the latent space. So in the latent space, you have now points that produce images with eyeglasses and points that produce images without the eyeglasses. You try to separate the two domains, and typically you use just an hyperplane. Okay, so you separate them with a linear model, and then the orthogonal direction to the latent space gives you the movement that you have to do, okay, in order to, for instance, add eyeglasses or remove eyeglasses. It depends, okay? The problem is, of course, when you have a lot of attributes, maybe editing one may change also some other attributes, maybe you are not interested in. You try to add glasses and you also change maybe the age, okay, of a person. That is not something that you would like to have. So, and this is called the entanglement between the features. You would like to have this entanglement. And so what you can do is you can try to project, okay, one movement with respect to the others in order to try to move. Okay, here you see I'm moving along this direction without changing the other one. So you can do these kind of operations in order to obtain a form of disentanglement behind the features. Okay, we are interested instead to doing something different. So we are interested in comparing spaces of different models. So what does it mean? Okay, well, the point is that surprisingly, other investigators, surprisingly, because there is such an amount of research that has been done, okay, on these models, and that is surprisingly that the problem has not been really addressed before, at least at my knowledge. So the point is the following one: given some latent representation of X in a given space, I am having a different models with a different latent space. We would like to find a direct way, okay, of mapping or passing from the latent representation of one space to the latent representation of another space. So this is the picture. Suppose for a moment, okay, that for any model we have both the encoder and the decoder. And so suppose this is the space, the latent space of the first model. This is the latent space of the second model. You see, in principle, we have always a way to pass from one to another one, because we start from a point here, we decode it into the visible space, and we use, okay, the other encoder to map it to another point of the other space. And we are interested to find a direct mapping between the spaces, a direct map. And of course, we hope, okay, to find a simple map, as simple as possible. The surprising fact, okay, really surprising, really is amazing, is that we can pass from a space to another one by means of a simple linear transformation in most cases.
So, question.
Yes?
The reason for trying to do that is clear from an intuitive point of view, because you want to get it directly. Do you think this would improve accuracy of correspondence?
I will give you in a moment my motivation for addressing this problem.
Okay? The event makes
no, I don't think. I mean, if you have, for instance, if suppose that this is a bad model and this is a good model, okay, I could start from a point here of a bad model, map it to the other space, use the other decoder to produce a really good point. Okay, so I mean, yes, in a sense, it's a way of also passing from, let's say, a bad model to maybe a more sophisticated model. Okay, so I don't know if that answers the question, but we shall see examples. Okay?
So I have another question, if I may.
Yeah.
I do not understand if we are comparing two different models, that is two different, for example, autoencoders, or one autoencoders and the second model you showed before.
I'm coming to that issue, okay? So please be patient. Okay.
Yeah.
So these are my motivations, okay, and it's also partially answered to your question. Okay. First question. Suppose that we have a given model. Do different trainings of the same generative model induce the extraction of the same features? Okay, so do different trainings, of course, different trainings of the same model result in different spaces? Do we have a way to pass from a space to another one in this case? Okay, we call this transformation as a transformation of type 1. Second question, do different architectural models driven by common learning objective learn the similar features? So what I mean, learning driven by common objectives, for instance, suppose I have two different variational encoders, and now I'm comparing the two variational encoders. Finally, what is the influence of the learning objective on the general representation? Because the learning objective of the generative adversarial network is completely different from the learning objective of the variational encoders. What is the influence that the learning objective is going to have on the features extracted and on the structure of the latent space? Okay, and we call this transformation as transformation of type 3. So if I was asked with this question before starting this work, I would have answered, yes, probably you can pass from a latent space to another one in the first case, even if I do not have strong reasons for claiming it, okay? I would have answered probably not in the other two cases, okay? The surprising fact is that the answer seems to be yes in all three cases, okay? In all three cases, we have simple ways for passing from the latent space of a model to the latent space of another one. The preliminary problem, how can we use a GAN? Because I said here we need a decoder and the decoder. And in the case of the generative adversarial networks, typically we only have the decoder. Well, the idea is that GANs can be inverted, okay? So you can train another network to produce the encoder. And it is a well-known, well-developed topic, okay? Inverting GANs. And for instance, here is our own inverter for the style GAN. So this is the original image. And here, okay, is the image that we obtain by re-encoding it by means of our encoder and re-extracting the information. And you see that they are almost identical. Please recall, okay, this image, this has been trained on the images generated by the style GAN. Really good, okay, as you see, the image that is produced by style GAN. And recall them because on different examples, we shall see that it's not working so well, okay? And we try to understand why. Okay, passing from a space to another. Okay, we compare the following models. So we had, we trained we trained a vanilla variational encoder, and we had for them 5 different trainings. Then we use a more state-of-the-art variational encoder. In particular, I used a variational encoder recently created by myself, but that works reasonably well. That is the so-called split variational encoder. And again, 5 different trainings, a vanilla GAN, and with 5 different trainings, and then finally a style GAN. These are very different models with different dimensions of the latent spaces. With 2 models have a latent space of dimension 64. We have this as a latent space of dimension 150. We have this as a latent space with dimension 512. And also they work at different resolutions, okay? For these 3 models, we work with relatively low resolutions, 64 by 64. In the state of the style GAN, instead you work with high resolution images with dimension 112, 124 by 124. And in all cases, we can pass from the latent space of another model to another one by means of a simple linear transformation. Transformation of type 1, okay? I show you the results. I hope you understand, okay, okay, usually I will show you this kind of 3 lines of pictures, okay? What does with 3 lines? Let me go back quickly to this image, okay? I start from the visible domain. I pick a picture here in the visible domain. This is my first line of images. Then I encode it into one of the models. And from starting from here, we have 2 possible paths. Either we decode it back, and this is the second line using the decoder of the model, or we map it to the other model and we decode it using the second decoder, okay? I mean, completely different path, okay? You cannot expect anything a priori, okay? I mean, it's really crazy, okay? This is the result, okay? This is the original image. This is the result obtained by the first decoder. And this is the result that we obtain by transforming it linearly to the other decoder and mapping it back. And you see, they are almost identical. Okay, when I was really surprised, okay, when I saw this kind of results, because I didn't expect them. Okay, even in these cases where you have very strange images, okay, still okay, you are producing the images that close enough, okay, close enough. Transformation of type 2, passing In this case, we are comparing two different variational autoencoders, a vanilla VAE and the more sophisticated VAE. You see, the vanilla VAE is not working particularly well, okay? It's not able to reproducing precisely the original image. And this is what we obtain starting from, I mean, we are losing a lot of information here, okay? And still now we map it to the other one, and we try, okay, to reconstruct an image. And we obtain images of better quality, even of course, maybe not in the direction, precisely in the direction of the original image. But still, okay, they are all very, very similar, okay? And these are two completely different variational encoders with completely different architectures. And so you see still, okay, the images are similar. Transformation of type 3, most complex one, between a generative adversarial networks, in this case, and the variational encoder. So this is, you see, I mean, they're similar, okay? You see, this is the original, this is what we obtained from the generative adversarial encoder. And starting from the latent encoding from all the variational encoders, we try to pass back to the space of the variational one and to reconstruct the image. And I mean, they are sufficiently close, okay? They're not precisely the same, okay? We have differences, but they share, okay, most of the structure and most of the information. In some cases, you see here, it's surprising because what you get by, for instance, the variational encoder, starting from the encoder produced by the generative adversarial network is much closer to the original than what the generative adversarial network was able to produce. But it's something, I mean, really astonishing. Okay, if we have a linear map between the domains, of course, I mean, in order to define a linear map, you just need a bunch of points of the same cardinality of the space you're working in, okay? And so we are interested to find these points. Of course, any set of points uncorrelated should work, okay? But since we have an approximation, we would like, of course, to choose our points in some sensible way, okay? Try to find them as separated as possible from the other ones, okay? So, and we call it a superset. And how can we define a superset? So this is the idea. Okay, so this is we define sectors in the spaces. This is the idea in three dimensions. Okay, so we define these sectors, and then we pick up points in these sectors in the space in order to be sure that the points we are interested, we are picking up are sufficiently distant one from the others. How do we choose the features? Well, we choose the features, first of all, choosing the most informative features according to the effect on the visible space. This is just the ordering of features in the case of the SPI, and you see there are relatively few latent variables that produce most of the modifications at the visible space. We just pick the 7 most interesting features, and we use these features to define a set of 2 to the 7 sectors in the latent space, and then we pick points in these sectors. So by the way, this is the effect of the features, the 7 most informative features on the latent space, on the visible space. You see, these are the kind of modifications that they produce. Most of them are, as you see, modification of luminosity, but changing it, okay, you change is at the same time the background, the color of the ears, the color of the skin, okay. Maybe there are some also rotations of the image. So, and I mean, these are very entangled features, but we don't care, okay? We are just pick the most interesting features. These are examples of elements in the same sectors. Of course, elements in the same sector shares the macrostructure of of the images. Okay, so this is sector 102, this is sector 109. Okay, and so you see very similar. Okay, in their shapes. And so we derive the superset in this way. Okay, these are examples of images in the superset, and the linear mapping, the linear transformation that we define between the spaces that I've been showing you before have been obtained using this kind of this small set of samples. Okay, we have 115 images. We define the mapping between the spaces using these 150 images. Okay, if I have a bit of time, okay, I would like to talk about some issues with the style gun space. So what is style gun? First of all, it's a famous network that was being created by people of the NVIDIA research team. And I do not want to enter in the details here of the architecture. It's a very relatively complex architecture. And in particular, I just would like to mention two facts. Okay, you have, in a sense, two latent spaces. Okay, in the style gun, we have the so-called real latent space where we pick points, but then this is transformed by means of a long sequence of transformations into another latent space, and the latent space with the same dimensionality. Okay, 150. The latent space where I'm interested here, okay, is this one. I'm working on the W space. All the semantic explorations for style gun are done on the W space. Okay. Of course, I will not expect this space to be linearly transformable into this other space, because otherwise, okay, it would not make any sense to have this long chain of transformations here. Very unusual, okay? It's the first network where I've seen the use of such a long chain of fully connected networks, fully connected layers. And okay, some problems with style gun. First of all, we have problems in inverting our supersets, okay? Oh, another point, okay. Style gun is all our models have been trained on a data set that is called Syllabi, and the famous data set, and with 200,000 images of famous people, okay? And instead, style gun typically is trained with a smaller higher resolution subset composed just of 30,000 images. So they are also different data sets, okay? So, okay. And one of the problems that we had working with style gun is that we had problem in inverting the superset. So we have these images, okay, that are taken from Syllabi, and we try to invert them into images, into the style gun, and you see the inversion does not work too well, okay? This is the original image. This is the image that we obtain after inverting it using our inverter. And so, I mean, yes, you have something of original images, some colors are preserved, some shape are preserved, but they are different images, okay? And here is another example. So these are examples of images in the superset, and these are examples of images inverted into the style gun. Second, so the guess was that these images, the images of the superset, are not in the latent space of the style gun. Can we confirm such a claim? Okay, we tried a different approach. What we can do is, instead of trying to use the inverted using the gradient descent technique, on the input, you have your output image, and you try to synthesize by gradient descent an input producing an image equal to the output image. So we tried this technique, gradient descent, and again, the gradient descent fails, okay? These are images in the superset, and when you try to produce similar images, starting with a style gun with gradient descent, well, the key is space, okay? You obtain this kind of results, but yeah, in some cases there possibly some similarities, okay? But then are not, okay, equal to the images that we get. So the guess, our guess is this one, okay, that the latent space of the style gun is somehow, okay, comprised into our superset, okay? Superset, the points in our superset are outside from the latent space of the style gun. Does this mean that we cannot try to invert? No, it just means that we cannot use our superset, okay? Of course, in order to be able to pass from a domain to the other one, you need points that are in both spaces, okay? So what we tried is learning by direct progression, starting from the latent space of the model. So you see, we do this operation, okay? Here we pick a random value from the latent space of the style gun, and here is the output produced by the style gun, okay? The first row is the output. Then we, starting from this image, we encode it, and using, for instance, a variational encoder, we produce a Z into the latent space of the variational encoder. And then we also have to crop differently the image, okay, because we also work with different croppings, okay, in the different models. So this is, we obtain Z. And then starting from this Z, we have two possibilities. Either we redecode back in, oh, this should be Z, sorry, it's not Y. Okay, so we decode using the decoder directly, and or we try to re-inject it, okay, into we are going to from style gun to Y, okay, or starting from W, we use our linear map, and then we use the variation decoder, okay, to decode the information. And you see, very similar, okay? It's good, okay? It's I mean, you can essentially, okay, pass from use the linear map to pass from directly from the latent space of the style gun to the code to the variational encoder. Even more interesting is the inverse transformation, okay? What we do here is something similar, okay? Here again, okay, we take a W from the latent space of the style gun, we produce an output, and we encode it, okay, with the encoder. And then here we go towards, okay, this is here, the result that we have here is again, okay, what we would obtain from SY using starting from this image. And here, instead, starting from this value Z, we map it with an inverse linear transformation towards the space of the style gun, and then we use the decoder of the style gun to obtain a different image. And I mean, they are almost identical, okay? You see, to the original images. So even in this case, okay, provided that you can find your analysis to points that you know, okay, that belong to the spaces you are interested in, well, you are able, okay, to define linear maps between them. Conclusions. We can pass from the latent space to another one by means of simple linear maps, preserving most of the content. Okay, I cannot claim that we get precise results, of course, it's not true, but we preserve most of the content of the image. So the organization of the latent space seems to be independent from the training process, the network architectures, also the learning objective, okay, done by shared same space. I mean, it's amazing, okay, because no matter, okay, what is your generative models, it seems to end up always with essentially the same information structured in the same way, okay? And the map can be defined by the small set of points common to the two spaces, okay, that we call the superset. And finding this points is, I think, an interesting operation per se. And second conclusion, in contrast with the usual belief, style gun seems to have serious generative deficiencies, okay? Many images seems to lie outside from the generative range of style guns. There are images that the style gun is not able to generate. And the generative process seems to be privileging standardization, eventually penalizing minorities and eccentricities. And to say other point important, more and more you hear, okay, or we can use our genetic model for doing data augmentation. No, come on, no, you cannot use generative models for data augmentation because generative models, all generative models so far still suffer from these issues, okay? And so using generative models for data augmentation is really the triumph of comfort. Okay? Okay, thank you very much.
Very interesting talk. Do we have any questions here from the audience? Valeria?
I have a couple of questions.
Please.
So the first one is whether the linearity of the map is a matter of simplicity or it turns out that nonlinear map would not give much better results.
Would you like also to repeat the question for the audience at home? I don't know if people home.
Okay, the question is if we try to investigate if we could improve, okay, the mapping, also studying, adding nonlinearities. And I think probably yes, but we didn't check yet. Okay, it's really a work in progress. We are still writing also the article, the paper. Okay, so I mean it's really something new. Okay, so it's something okay what we plan to do, but we didn't try it.
So the other question is about the sets, the support sets. And it's not clear to me how you, since they are so important to the two common different spaces, they are common to different spaces. So how you select these support sets? I'm not sure I understood.
Okay, for the syllable data set, we just try to choose points sufficiently distant from each other. Okay, in order to choose this point distant, we use this technique. Okay, first of all, we select the most important features that we have in our Latent space, and here is the ordering that we have for our features.
So how do you choose these features?
The features, we use them by measuring the effect that they produce on the visible space, okay? In the sense that for each feature, we take a set of samples. We consider the images produced by these features in the visible space. And then one feature at a time, we zero out it, okay? We put it at 0, and we measure the change that we have at the visible space. Okay, and so we take, and you see there are only relatively few features that really produce strong modifications at the visible space, and we just pick up these features, and
So
we use
specific application, images or faces. Does it mean that some of the face features are more relevant than the others, like the eyes, nose, typical?
It's not, okay, these are the features, and these are the modification produced by man, okay? You see, it's not related to eyes, nose, colors of the ears. Yeah, okay. This is modification, okay, produced by each feature. Okay, this is most important feature, right? The feature that produces the most sensible modification at the visible space. Okay, and you see the modification is less, in a sense, it's less that we could expect. Okay, but we have a lot of, I mean, from as a distance between the images, here and here, there is a lot of distance because you change the color, okay? You pass from a very light image to a relatively dark image, okay? So this is the kind of modification that is produced by these latent variables. And also similar, okay, here, essentially all of the features are essentially changing the light of either the whole image or the part of the image, okay? Here you see you are changing the background. Here you are changing the background in this part, okay? So these are the kind of modifications that are produced, typically.
Okay.
So,
There are online questions.
okay.
So there's an online question. I think Antonio was first.
Please just speak up.
Yes. Hi. Thanks, Andrea. Super interesting talk. I was wondering if, so it seems to me that you are essentially measuring the effect of mapping the one latent space onto another by looking at the decoded images, right? So looking at differences, in a sense, in the observable space. Would it also make sense to perform some sort of like manifold different analysis in the latent spaces? So for example, you could try to see if even the pairwise distances between the latent codes are somehow preserved across the different latent spaces, right? So it's not only rotating them by your linear map, but does it make sense?
Yes. Okay.
I left, they didn't at all.
Okay. The question is, but I think it's not. I mean, okay. The question is if I'm measuring, okay, the mapping by the quality of the resulting images. Okay. Yes, because I think it's what we are interested in, but that is not the way I define the mapping, okay? When we define the map, okay, we just try to minimize the distance in the latent space, okay? So we take a set of points here, we transform it into a set of points of the other domain, in the other space, looking, okay, making this kind of transformation that is always possible, okay? So you have a set of points in the first space, a set of points in the second space, and we just try now to compute the mapping, okay? Minimizing the distance in the latent space, not in the visible space. That is amazing, okay? In the result, that by minimizing this distance and defining this map in the way, okay, it should be defined, we obtain such a good result in the visible domain.
There is a follow-up to this by Ilias, which relates to what you're explaining right now. He was asking, how do you find M then? So after you've selected the point, let's say left and right.
Okay, precisely in this way, okay? So you have your set of points here. You can also find the same set of points, the corresponding ones in the other space, passing through visible space, and then you try to compute the map.
By solving a linear system.
By solving a linear system. Right.
I assume this answers Ilias's question.
The only thing, okay, I just forced the bias to be 0, so I'm defining, I don't know, there is a mathematical name for, I don't think it's a rotation because you can have scaling, okay, but the fact that the bias is 0, so we cannot move, we don't move the origin. I don't know if this kind of transformation as a, so it's not a really a fine transformation, okay, it's not even a rotation, but.
Yes, so I found that really interesting your talk. I can go back to the picture where you had the perpendicular, you know, they move the direction.
This one.
Right. So first of all, I want to say that
this is not my work. It's not. It's something.
No, but I like your philosophy that if you have generative networks, they're not about computation. They're very different things. In fact,
isn't this related to the fact that when you move in that direction, you don't really know if you are creating images that are really truly could be in the data set. You really generated new things. Am I right in saying this, or am I not understanding the point?
No, that's right. Okay, that's right. It's a possibility. Okay?
Yes, the other thing I wanted to ask you is about the adversarial attacks, because that's the other side of the coin, right? I mean, when you are looking at the generative models, somehow you could use them to avoid adversarial attacks. Have you thought about possible application? Is there an obstacle with the...
I'm not sure to understand the question.
So you could have direction where you move, and the algorithm is really sure that that's a class, but you get something that is totally meaningless. I mean, there are famous things on Google, for example, of that. And maybe if you do this, it's not true that you augment your data set, but you could help to protect against adversarial attacks.
Okay. So in the case of style gun in particular, this is something that is very difficult to obtain, in the sense that you can make more or less any movement, okay, in the latent space, and usually it results
I see.
in a good image.
So it will not protect you against that.
No, no.
Because that's a big problem. To create a
In some
network which is
cases,
robust with respect to this type of attacks. But okay, thank you. It was an application.
Do you have any other questions? Okay. If not, I'd like to thank Andrea once again.